Okay, so we're going to talk about oxidation and reduction in this video. So to understand this, first we're going to look at what oxidation is. So oxidation can be slow or rapid. If you're talking about a slow oxidation, that may be the rusting of iron. If you're talking about the rapid oxidation, you may think about your Bunsen burner flame. And so what's common here is that both of them involve the use of oxygen as a reactant. And that doesn't mean that every oxidation reaction will have oxygen, but that's where we get the name from. So if we're talking about oxidation and reduction, we need to remember that oxidation and reduction go together because oxidation is a loss of electrons and reduction is a gain of electrons. They're actually the same electrons that are lost are gained in the same reaction. So that's why oxidation and reduction go together. If you're going to gain some electrons, they have to be lost from somewhere else. So if one substance loses, another substance must gain in the same reaction, otherwise it can't occur. So we call this thing together redox for oxidation, reduction, reduction, oxidation, redox. That's just the nickname that we give for it. Another term that we're going to see is reducing agents and oxidizing agents. So the reducing agent is the substance that gets oxidized because it's reducing the other substance. The oxidizing agent is the substance that's getting reduced because it's oxidizing the other substance. So if hydrogen is the reducing agent, then what's getting reduced? The oxygen is getting reduced. If oxygen is the oxidizing agent, then it must be oxidizing the hydrogen. And so you can think about the agent as the opposite of what's happening to that thing. That is the agent that it is because it's doing the opposite to the other reactant. Your agents always must be reactants. So agents are always reactants. Be sure to write your agents exactly as it's written as reactants, not as like an element. Don't just say H, say H2, for example. So a way that I can remember this is to say that Leo goes Gur. So Leo is a cute little baby lion, and so we consider Leo a positive change, and Leo stands for losing electrons oxidation. And then Gur is a negative change. If you hear a lion growling at you, that would be negative. And so we say gaining electrons reduction for Gur. So what you need to do is you need to decide what's happening to your substance in the reaction. Is it undergoing a positive change, meaning its charge or its oxidation state is getting more positive? Then it would be Leo oxidation. If it is getting more negative, it would be Gur reduction. And this makes sense because if I lose electrons, don't I become more positive? And if I gain electrons, I become more negative. So how can we tell this? We have to look at oxidation states. So oxidation states are essentially the charge an element would have if it had a charge. So when I'm assigning an oxidation state, I don't mean that it does have a charge. So we can assign oxidation states to covalent compounds, but it's just if it were to separate, if it were to become charged, this is the charge it would have. And so when we are talking about ionic compounds, the charge and the oxidation state are the same. But when we're talking about covalent compounds, we have to really look at what the charges would be, and we still need to think about how we're adding up to a neutral compound or adding up to the charge of an ion. So this list is hierarchical, which means that you want to make sure you start at number 1 and then you go down the list as you're assigning states in your chemical reaction. The first thing that you're going to look for is a free element. A free element is an element that is not bonded to anything else. So it does not have anything that it's bonded to. It's just chilling as its normal elemental thing. So like hydrogen would be H2, oxygen would be O2, iron would be Fe. The oxidation state of any of those elements that are not bonded to anything else is 0. So assign those first. If you have a monatomic ion, monatomic meaning one atom, then you will have a charge there. The oxidation state is just the same as its charge. So for example, if you have sodium ion hanging out, the oxidation state would be +1. So here an example would be H2 or Fe. The sum of the oxidation state is either 0 or the charge if it's a poly. And this is the same for ionic compounds, the same thing we've done for all of our ionic compounds is we made sure that they added up to 0, right? So the only thing that's a little bit different here is that a polyatomic ion is equal to the charge of the ion. So if I have a polyatomic ion like phosphate, everything, so my phosphate plus my 4 oxygens would have to add up to -3 together because the charge of phosphate is -3. Then when you're looking about inside compounds, okay, so we've talked about free elements, monatomic ions, and okay, everything's got to add up to a certain number. And then inside that compound, how can we give oxidation states to see that it adds up to 0 or to see that it adds up to the charge? So first you're going to look for group 1 and group 2 metals. Group 1 metals always have +1, group 2 metals always have +2. You know that these are type 1 metals. And so we can actually include aluminum, gallium, zinc, cadmium, and silver in this category. Any type 1 metal gets their charge, right? But then we know that already. So oxidation state for ionic compounds, just give it the charge. You know it's going to add up to 0 because you wrote the compound correctly. Then once we get into nonmetals, we kind of have a list that we need to follow. First, you're going to look for fluorine. If you have any fluorine, it always gets -1. For hydrogen, it's a little bit more confusing. Hydrogen as a nonmetal is always at the end of the compound. For example, CH4. Okay, hydrogen at the beginning is acting as a metal, like an HCl. Hydrogen gets a +1 here. So you really have to understand that in the list here, hydrogen is acting as a non-metal. So it's going to be hanging out at the end of the compound. So hydrogen in NH3 would be -1. Hydrogen in CH4 would be -1. Oxygen is your most important guy here. You're going to see the oxygen most often, and so really I'm going to highlight this for you. Oxygen is the most important one to remember. If oxygen gets 2, then everybody else kind of has to be whatever it needs to be to make sure oxygen gets 2. Exceptions to this would be with peroxides. Peroxide, if it adds up to -2, each oxygen has to be -1. And then anytime you have oxygen with fluorine, the fluorine's going to take precedence. But most of the time you're going to see oxygen not in peroxide and not with fluorine, and so we should just assume that oxygen always gets a -2. So out of these things on the list, I would say know that oxygen gets -2 more than anything else in this list, and then that's going to be your most common oxidation state that you need to look at. After you look at oxygen, you can do the regular charges for nonmetals, right? So -1 for the halogens, -2 for the oxygen group, -3 for the nitrogen group. But again, if I have oxygen or fluorine or hydrogen hanging out, something in group 7 might have to be positive. Something in group 5 might have to be positive, because you have to think about this list as hierarchical. So top gets their say first, and then everything else kind of may have to change depending on what the top element wants. So here's a lot of rules. Let's just look at it. So we're going to use oxidation states in this reaction to identify an element that's being oxidized and an element that's being reduced. So go ahead and pause, look back to your list, and see what you can find. Okay, so hopefully you kind of gave this a shot. First, we're going to identify the oxidation states. Do you see any free elements? That's first on the list. So free elements are the calcium and the hydrogen. These are our free elements. They have an oxidation state of 0. So I'm going to put my oxidation states underneath. Usually we'll write charges on the top, right, if I want to figure out that out. So I'll write charges up here, write ions up here. There's no ion for calcium, the free element. It is not ionic, so there is no ion for it. So I'm not going to worry about that. But if I have an ionic compound, I can break it down into its ions up here. Oxidation states I'm going to put on the bottom. You can put it wherever you want. And so that means hydrogen's also a 0. So now let's look at water. Pay no attention to coefficients. So just like when we're doing molar masses and when you're writing chemical formulas, we don't really pay attention to the coefficients, so don't worry about that. So here for water, this is a covalent compound, so I'm not going to put any ions, but oxygen always gets what? Always gets -2. So hydrogen is in the front here. It's not acting as a nonmetal, so it doesn't come above the hydrogen or the oxygen. So I have to look and see, what does hydrogen have to be in order for this water to add up to what? What's the charge of the water? The charge of the water is 0 because it's not a polyatomic ion. It's a neutral compound. So if I have to take the water and add it up to 0, I have 2 hydrogens. I need to know what they have to be, plus 1 oxygen with a -2 state has to add up to 0. So I have 2x minus 2 equals 0. And so therefore x is equal to +1, so each hydrogen is +1. So now we can come over here to this ionic compound. If it's ionic, it may be helpful for me to split it apart into its ions. If I split it apart into its ions, I can just assume the oxidation state is going to add up to the charge of the ion. So for calcium, the charge of calcium is +2. Therefore, the oxidation state is +2. Now for hydroxide, I have a little more work to do. It has to add up to -1 because that's the charge. So I have 1 oxygen. We know oxygen has to be -2. And then the hydrogen has to be what? I know hydrogen's at the end here, but just go with the oxygen rule in this case. You'll see that it'll add up to a -1. If hydrogen is acting as a negative here, then oxygen can't be -2, and that's really not the way that oxygen likes to be. So I have -2 plus x equals -1, so x has to be equal to +1. So I have oxygen here is -2, and hydrogen is +1. And so we need to also determine what's being oxidized and what's being reduced. So let me erase my work here. And now I'm going to look at what's going on with each of these elements. So let's check out calcium. So on the left side, calcium has an oxidation state of 0, and it is moving to an oxidation state of +2. That is getting more positive. And if you remember, getting more positive is Leo, and Leo is oxidation. So the calcium is undergoing oxidation. Let's look at hydrogen. Hydrogen is going from +1, and then I see hydrogen in 2 places. I can see +1, or I can see 0. If you see one that's changing, let's focus on that one. So if hydrogen is going from +1 to 0, it's getting negative. So that's GR. So that's reduction. So the hydrogen is getting reduced. If you want to check, let's look at the oxygen. The oxygen is going from -2 to to -2, no change. It is not being oxidized or reduced. So if something is being oxidized, can you tell me what kind of agent it is? The oxidation is the reduction agent. So calcium is reducing hydrogen, so it is the agent of reduction to hydrogen. And the hydrogen is oxidizing the calcium, so it is the oxidizing agent. So you kind of have the opposite of whatever is happening to it. That's the agent that we call it. The question didn't ask for that, but it's good practice just to work that out. Okay, so we're going to look at balancing, reduction, or redox reactions. For balancing redox reactions. In Chem 10, we are only going to cover the very bare minimum of this topic. We're not going to be covering, sometimes in your textbook it's going to show you what to do in acidic or basic conditions. We're not covering that in detail. That's going to be for the next level. We're just going to do very simple balancing. So when we balance redox reactions, we have to make sure that our charges and our electrons are balanced. And so we are not so much concerned, we are concerned with the balancing of the elements, but we really need to kind of open the reaction up and look and see what's happening to the transfer of electrons here. And that's important because if I'm talking about building a battery or analyzing any sort of electrical thing, knowing the number of electrons transferred in a reaction can be very helpful for me to find out the voltage, the current, and all of these things. And so we're kind of going to crack these reactions open and figure out what's happening to their electrons. So for this reaction, we have aluminum reacting with a silver ion to create aluminum ion and a silver solid. Now keep in mind, this is a net ionic reaction. So if this is a net ionic equation, there's a spectator that's not here. So you don't need to worry about that. It's already been canceled out for you. If you see a spectator happen in your reaction when you're trying to balance it, just cancel it out. So a spectator is an ion that is the same on both sides. We have an ion here. We don't know what it was, but it doesn't matter because it's not changing. So first, we have to figure out which is being oxidized and what's being reduced. So the aluminum is free, so it starts as 0. The silver is a monatomic, so its oxidation state is +1. The aluminum is monatomic with a state of 3, and the silver over here is 0. So the aluminum is going from 0 to +3, so that's oxidation because it's getting more positive, so that's Leo. And then the silver is going from +1 to 0, that's getting more negative, that's reduction, that's Gur. Now we're going to divide the reaction into two half reactions. So we decided that this is oxidation, and so pull down anything that has to do with the oxidation. So it's the aluminum and the aluminum. The reduction, the silver and the silver. Okay, and we're just kind of pulling it down, but we're separating it out into what we call half reactions. So now once you have your half reactions, we're going to balance each type of atom. I see that I have one aluminum atom, one aluminum, one silver, so that's done. Then I need to add electrons to the more positive side. So let's look at this top reaction. What's the total charge of the left side? The total charge is 0. What's the total charge of the right side? +3. Which side is more positive? This side is more positive. How much more positive is it? Well, it's 3 positive, so I have to add 3 electrons to balance it out. We cannot add protons, we cannot remove electrons, we can only add electrons, and we want to do that to the more positive side. And so, if we're looking at this bottom reaction, the reduction, I see I have a charge of +1 on this side and 0 on this side. So the +1 side is the more positive side. And so how much more positive is it? It's 1 more positive, so I'm going to add an electron to the left side. So here you can see that I have this. I should have 0 charge on both sides of each reaction. Okay. You just need to make sure that you have a balanced charge. It doesn't always have to be 0. It just needs to be equal charge on both sides. That's why we say pick the more positive side and make it equal. So here's what your two-half reactions will look once we add those electrons. So we can see that electrons are being made here and they're being used here. But electrons are being made, 3 electrons are made and only 1 is used. Well, that's not the way it's going to work, right? Because if there's 1 silver ion, aren't there billions and billions and trillions of them? Yes. So if I'm making 3 electrons here, I'm going to be using 3 electrons here. So I need to correct that. I need to correct for that in my model. So the last step, we need to make sure that we have the same number of electrons on all sides. So if I have 3 here and I only had 1 here, I need to multiply this whole reaction by 3. And so I can rewrite that. I will say 3 electrons plus 3 silver gives me 3 silver, and I'll cross this out so that what I'm really looking at are these 2 reactions for my last step. And my last step is going to be to add the half reactions together. And so literally we set it up like an old school addition problem. Put your arrows in the middle of both, and then we're going to cancel out our electrons because I know that there are 3 electrons transferred. That may be helpful to me in a multiple choice question or in a question about electrochemistry later in another chemistry class. But once I figure that out, electrons, they're being transferred. So they go as a product, they come out as a product, they get used up, so I don't want to include them in my overall reaction. And so you'll see that I have here the real balanced equation, 3 silvers. And so if I look at my initial equation, if you didn't know how to balance the redox, you would have said that this was balanced. 1 aluminum, 1 silver, 1 silver. But if you look closely at the charges are not balanced. And so I would have to add 3 silvers and 3 silvers to balance all my charges. So that's essentially what I'm doing, but I'm kind of taking a deeper look into what's happening with my electron transfer here. So we do a quick little check at the end to make sure our charges are balanced, to make sure our elements are balanced, and then we're done. So why don't we go ahead and do a practice. So you're going to balance the following reaction using a half reaction method. So sodium bromide solution reacts with chlorine gas to produce sodium chloride and liquid bromine. So take a pause here and try this one out. Oops. Okay, so we started with sodium bromide. So sodium has a charge of +1, bromine has a charge of -1, and so I get, oops, I'm not going to balance this today. So I get sodium bromide aqueous. Here, let me change the paper, it's kind of... Okay. Sodium bromide aqueous, and it reacts with chlorine gas. There's no charge for chlorine gas, it's just chlorine gas. Remember, I only break apart, I only have ions for aqueous things. And then I make sodium chloride. Notice that I'm still doing my ions up here, even though I kind of know sodium chloride is NaCl. I want to make sure I always get my ions correct, especially on an exam or a quiz. And then I have bromine as it exists naturally, which is in the liquid form. So I need to assign oxidation states first. So sodium, let's change colors here. Sodium has a +1 because it's an ionic compound. You just use your charges. Bromine has a -1, and chlorine is a free element. Sodium here has a +1, chlorine has a -1, and bromine here is a free element. So I have all my oxidation states assigned, so now I can see what's being oxidized and what's being reduced. So let's check it out. For sodium, it's going from +1 to +1. This is no change. If it's an ion, we're going to call it a spectator. So what we're going to do when we write our final equation is we're not going to include sodium ions. Let's look at bromine. It goes from -1 to 0. That's getting more positive. So that's Leo. So that's oxidation, which means that bromine is the reducing agent. Now technically the agents are the full compound, and so we would say the agent is sodium bromide in this situation. You can also say that sodium bromide is getting oxidized. That's fine, but technically if the question's asking you for which element, you should state the element by itself. So then we have chlorine. It is going from 0 to -1. That's getting more negative. So that's GR. So that's reduction. So that means that the oxidizing agent is the chlorine gas. And so now we know what's being oxidized or reduced, we can write our half reactions. So to write our half reactions, we can say our oxidation reaction has anything to do with oxidation. We're going to exclude our sodium ion because it's not changing, and it's because it's ionic. We don't have to write it because this does exist like this, or it doesn't exist together, really. So it's really bromine going to bromine. My reduction is chlorine going to chlorine. Okay, so first I need to balance my elements. Oops. Sure. I need 2 bromines on this side, and I need 2 chlorines on this side. So balance our elements first. Now we have to look at the charge on both sides so we can balance the charge out. On this side I have a -2 charge because I just added 2 bromines, and a 0. Which side's more positive? The 0 is more positive. How much more positive? 2 more positive. So add 2 electrons to the right side of this reaction. Here I have 0, -2. This side is more positive now, so I'm going to add 2 electrons to this side. So rewriting our equations, we have 2 bromides goes to bromine plus 2 electrons. Here we have 2 electrons plus chlorine makes 2 chlorides. If I'm trying to cancel my electrons out, they are both 2, so I don't have to do anything like we did in the previous example. I can just cancel it out. And so my total reaction is 2 bromide plus chlorine makes bromine plus 2 chloride. If I wanted to throw the sodium back in, I totally could. I could say 2 sodium bromides plus chlorine gives me bromine plus, oops, I'm sorry, you're not seeing this, huh? Let's extend this down. Sorry about that. And so I'm just adding the sodium back in to make 2 sodium chlorides at the end. The reason why I don't include the sodium when I'm balancing the half reaction is because if I'm looking at the half reaction here, if I have sodium hanging out on this side here and I don't have it on this side, that's going to be really confusing for me to have to balance my elements, and so I just kind of exclude it when I'm dealing with a single replacement reaction with an ionic compound. So that's something that you can do. There are ways to deal with water and hydrogens and oxygens in water, but you're not going to have to deal with that in this level of chem. Okay, so that's all about oxidation and reduction, and I hope that helps.